Hi everyone! I hope you are all fine and well. My name is John Wynford Bahan, and I'll be discussing about ocean thermal energy conversion. These are the learning outcomes. First, to discuss the discovery of ocean thermal energy conversion. Second, to discuss the theory of ocean thermal energy conversions. Lastly, to describe the different ocean thermal energy conversions. What is ocean thermal energy conversion? Ocean thermal energy conversion generates electricity indirectly from solar energy by harnessing the temperature difference between the sun-warmed surface of tropical oceans and the colder deep waters. In order to produce power with a low temperature range, a working fluid with low boiling point is used. This is an example of an ocean thermal energy conversion. In this figure, working fluid is being pumped to the evaporator. Then, the heat of the warm surface seawater evaporates the working fluid into a gas. Pressurized working fluid in gas state drives the turbine to produce power. Then, the cold deep seawater returns the working fluid to liquid state, and the cycle goes on and on. About working fluid, these are the popular choices. First is ammonia, which is commonly used as a working fluid. It has superior transport properties, easy availability, and low cost. However, it is toxic and flammable. Next is the fluorinated carbons such as chlorofluorocarbons and hydrochlorofluorocarbons are not toxic or flammable, but they contribute to ozone layer depletion. Hydrocarbons are highly flammable. In addition, this would create competition for use of them directly as fuels. The power plant size is dependent upon the vapor pressure of the working fluid. With increasing vapor pressure, the size of the turbine and the heat exchangers decreases while the wall thickness of the pipe and heat exchangers increase to endure high pressure, especially on the evaporator side. What is the origin of ocean thermal energy conversion? In 1881, the idea of ocean thermal energy was first proposed by French physicist Jacques-Alcin d'Arsonval in an 1881 Revue Scientifique article. He envisioned a closed-cycle heat engine with ammonia as the working fluid but never tested it. In 1926, Georges Claude, the student of d'Arsonval, designed an open-cycle system using his personal funds. It is derived from his invention of the neon light. He built an experimental system in 1930 at Matanzas Bay, Cuba. The system used a cold water pipe 1.6 meters in diameter and 2 kilometers in length to successfully bring cold seawater from a depth of more than 700 meters. In the same year, Claude's system generated 22 kilowatts of electricity by using a special low-pressure turbine. However, the system operated on a temperature difference of only 14 degrees Celsius and consumed more power than it produced. Unfortunately, in 1935, a storm destroyed Claude's cold water pipe only a few days after the Matanzas Bay experiment began. In 1935, Claude began constructing another open cycle plant, this time aboard a 10,000-ton cargo vessel moored off the coast of Brazil. Sea waves ripped apart the cold water pipe during installation. Nearly bankrupt, Claude was forced to stop work. He never achieved his goal of producing net power from an open cycle Otech system. But he did demonstrate that it is possible to integrate all the components into a working system. In the year 1956, Claude's work influenced the French government to continue research in open cycle ocean thermal energy conversion. In 1956, a French team designed a 3 megawatt open cycle plant for Abidjan on Africa's west coast. The team built a cold water pipe that was 2.5 meters in diameter and 4 kilometers long. But it proved too difficult to deploy. Completion of the plant was also hindered by competition with inexpensive hydroelectric power. From 1972 to 1977, the current Federal Ocean Energy Technology Program began in 1972 as the Ocean Energy Systems Program and was sponsored by the National Science Foundation. It was transferred to the Energy Research and Development Administration in 1975, which became the U.S. Department of Energy in 1977. The OET program, directed by DOE's Wind and Ocean Technologies Division. The mission of OET program is to develop ocean energy technology to where the commercial sector can assess whether the technology offers viable energy conversion alternatives or supplements to system currently in use. Current research activities on components and small-scale experiments support this mission. In the year 1979, DOE's OET program activities are founded on a strong base of research and development. This base was used in 1979 when the state of Hawaii and Lockheed Corporation, with engineering and construction support from the Dillingham Corporation, built the first closed-cycle demonstration plant of ocean thermal energy conversion that produced a net output of electric power. In the figure shown in the next slide, Mini Otech was a closed-cycle plant mounted on a converted U.S. Navy barge moored about 2 kilometers off Keyhole Point. Mini Otech used a cold water pipe measuring 0.46 meters in diameter and 800 meters in length to produce 52 kilowatt gross and 15 kilowatt net output. In 1980, DOE completed the construction of Otech One, a testbed for closed-cycle ocean thermal energy conversion heat exchangers installed on board a converted U.S. Navy tanker. Results from Otech One confirmed the methods that can be used to design commercial-scale heat exchangers. The test results demonstrated that Otech systems can operate from slowly moving ships and with very little effect on the environment. The Otech One Experiment, the first integrated system in DOE's test program, was successfully concluded in 1981. In 1981, several countries seized the potential of ocean thermal energy conversion as a renewable energy option. Outside the United States, Japan has had the most active Otech program. In 1981, the Tokyo Electric Power Company and Toshiba built a 100 kilowatt gross closed cycle plant in the Republic of Nauru in the Pacific Ocean. This cold water pipe has 945 meters in length, laid on the sea to a depth of 580 meters. The plant used Freon as a working fluid and titanium shell and tube heat exchangers. Although the Nauru plant was rated for a 14.9 kilowatt net output, it surpassed engineering expectations by producing 31.5 kilowatts of net power during continuous operating tests. From 1985 to 1989, based on a careful evaluation of past activities, the Ocean Energy Technology Program strategy from 1985 to 1989 has been focused on the technology that would allow industry to develop a 2 to 15 megawatts nearshore or land-based open-cycle ocean thermal energy conversion system. In 1992, the first program priority is to prove the feasibility of open-cycle Otech, which is being pursued through a net power producing experiment, scheduled to begin operation in 1992. The experiment will be used to validate the computer models used in designing the NPPE. The experiment will be built at DOE's Seacoast Test Facility, located at the Natural Energy Laboratory of Hawaii, at Keyhole Point on the Big Island of Hawaii. This is the Natural Energy Laboratory of Hawaii showing DOE Seacoast Test Facility at the bottom center. DOE and the state of Hawaii have jointly developed the capabilities needed to pump cold and warm seawater at this site, permitting testing of the open cycle system's heat and mass transfer processes. A database will be developed documenting how key components, such as the evaporator, condenser, mist eliminator, derailleur, and turbine, perform in seawater environment. Materials performance and fabrication and installation techniques will also be evaluated. Activities completed in recent years include designing, fabricating, installing, and operating a heat and mass transfer scoping test apparatus at the Seacoast Test Facility. This apparatus validated the seawater performance of spout evaporators and direct contact condensers crucial to open cycle Otech system performance. It also demonstrated for the first time in the OET program that a prototype open cycle Otech system using a surface condenser can produce desalinated water. This is the figure of the heat and mass transfer scoping test apparatus at the Seacoast Test Facility. In 2002, India tested a 1 megawatt floating ocean thermal energy conversion pilot plant near Tamil Nadu. The plant was ultimately unsuccessful due to a failure of the deep sea cold water pipe. Its government continues to sponsor research. In 2006, Mackay Ocean Engineering was awarded a contract from the U.S. Office of Naval Research (ONR) to investigate the potential for Otech to produce nationally significant quantities of hydrogen in at-sea floating plants located in warm tropical waters. At the same year, realizing the need for larger partners to actually commercialize Otech, Mackay approached Lockheed Martin to renew their previous relationship and determine if the time was ready for Otech. And so, in 2007, Lockheed Martin resumed work in Otech and became a subcontractor to Mackay to support their SBIR, which was followed by other subsequent collaborations. In March 2011, Ocean Thermal Energy Corporation signed an energy services agreement with the Bahamar Resort, Nassau, Bahamas, for the world's first and largest seawater air conditioning system. In June 2015, the project was put on pause while the resort resolved financial and ownership issues. In August 2016, it was announced that the issues had been resolved and that the resort would open in March 2017. It is expected that the SWAC system's construction will resume at that time. In 2011, Mackay Ocean Engineering completed a heat exchanger test facility at Nelha. Used to test a variety of heat exchange technologies for use in Otech, Mackay has received funding to install a 105 kilowatt turbine. Installation will make this facility the largest operational Otech facility, though the record for largest power will remain with the open cycle plant also developed in Hawaii. In July 2011, Mackay Ocean Engineering completed the design and construction of an Otech heat exchanger test facility at the National Energy Laboratory of Hawaii. The purpose of the facility is to arrive at an optimal design for Otech heat exchangers, increasing performance and useful life while reducing cost. And in March 2013, Mackay announced an award to install and operate a 100 kilowatt turbine on the Otech heat exchanger test facility and once again connect Otech power off the grid. In March 2013, Saga University, with various Japanese industries, completed the installation of a new Otech plant. Okinawa Prefecture announced the start of the Otech operation testing at Kome Island on April 15, 2013. The main aim is to prove the validity of computer models and demonstrate Otech to the public. The testing and research will be conducted with the support of Saga University until the end of the fiscal year 2016. IHI Plant Construction Co. Limited, Yokogawa Electric Corporation, and Senesis Incorporation were entrusted with constructing the 100 kilowatt class plant within the grounds of the Okinawa Prefecture Deep Seawater Research Center. In July 2014, DCNS Group, now called the Naval Group, in France, partnered with Aquo Energy announced NER 300 funding for their NEMO, New Energy for Martinique and Overseas project. If successful, the 16 megawatt gross, 10 megawatt net offshore plant will be the largest Otech facility to date. DCNS plans to have NEMO operational by 2020. In 2015, an ocean thermal energy conversion power plant built by Mackay Ocean Engineering went operational in Hawaii in August 2015. This is the first true closed-cycle ocean thermal energy conversion plant to be connected to a U.S. electrical grid. It is a demo plant capable of generating 105 kilowatts, enough to power about 120 homes. In July 2016, the Virgin Islands Public Services Commission approved Ocean Thermal Energy Corporation's application to become a qualified facility. The company is thus permitted to begin negotiations with the Virgin Islands Water and Power Authority for a power purchase agreement pertaining to an ocean thermal energy conversion plant on the island of St. Croix. This will be the world's first commercial Otech plant. There are three types of Otech systems, namely closed cycle Otech systems, open cycle Otech systems, and hybrid Otech systems. First is the closed cycle. In this system, heat transfer from the warm surface seawater occurs in the evaporator, producing a saturated vapor from the working fluid. Electricity is generated when this gas expands to lower pressure through the turbine. Latent heat is transferred from the vapor to the cold seawater in the condenser, and the resulting liquid is pressurized with a pump to repeat the cycle. Second is the open cycle. In this system, steam is generated directly from the warm seawater as the working fluid. Warm seawater is flash evaporated in a partial vacuum in the evaporator. The vapor expands through the turbine and is condensed with cold seawater. Third is the hybrid. Hybrid cycles combine the potable water production capabilities of open cycle with the potential for large electricity generation capacities offered by the closed cycle. These are the currently operating Otech plants. First is the Mackay Ocean Engineering and Okinawa Prefecture Deep Sea Water Power Generation Demonstration Project. First is the Mackay Ocean Engineering located at Kailua Kona, Hawaii, USA. It is a closed-cycle Otech system. Mackay Ocean Engineering closed-cycle ocean thermal energy conversion works like this. The working fluid liquid is being pumped in the evaporator. Using warm water intake, it will vaporize the working liquid. The working fluid vapor will go to the turbine to generate electricity, and the working fluid will go to the heat exchanger condenser. Using the cold water intake, it will condense the working fluid into liquid, and the cycle goes on and on. Okinawa Prefecture Deep Sea Water Power Generation Demonstration Project is located at Kume Island in Japan. It is a closed-cycle Otech system. It is also closed-cycle ocean thermal energy conversion, relatively has the same process in the Mackay Ocean Engineering. Thank you very much, God bless, and stay safe.